morning, sir.
Good morning. How are you guys today? Okay, guys. Let me start with this one. Matthew Alberston. Matthew. Hello.
He's trying to say he's here, sir.
He's here.
Sir.
I can't hear him. Matthew Alberston. Can you hear me? Can you hear me? Matthew.
Sir, he's saying yes.
I can't hear him. I can't see him. Matthew Alberston. Okay.
He's here, sir. I don't think he can hear you. Yeah, his mic's not working, but he's here.
No, but I want to talk to him. I want to talk to him.
Right, but his mic isn't working, so he's not able to.
Then why is he here? If he's serious, his mic doesn't work. Just ask him, when did he submit his exam? He did not submit his exam till yesterday night. So he missed the time. Just convey this message to him. Okay, then second is, if he thinks that he can submit the exam whenever he wants, that's not going to happen. Is there Reese Simon?
Yes, sir.
Our class time is 7:45. You know this thing, right? Okay, guys. So let's start with the next article. I think you can see my screen, right? Yes, sir. Yeah. So next article, these are the last two applications in our syllabus for the integration, last two applications of integrations, and one is work done, very practical application, and second one is the fluid force. So article 7.5 and 7.6, these two articles are left out in this chapter, and then after we will be switching over to the last chapter, and that is the sequence and series, infinite series, you can say. So let fx be a continuous function of the closed interval a to b, describing the amount of force being applied on an object in the direction of the travel from distance x equal to a to x equal to b. The total work W done on AB is W equal to integration fx dx, x runs from a to b. That means suppose I have something, just look at over here, just try to look at over here. Suppose I have this cell phone, right? And if I apply some force over here, that means this object, this is just one object. This is just moving like this. Look at over here. So whatever the force I'm applying over here, whatever the work done by this object, right? That's what we mean by the work done. And that work done is given by W is equal to integration a to b fx dx. There are two units for work done. Yeah, in UK, United Kingdom, people are using the first unit that is called SI unit, the unit of force in Newton kilogram meter per second square, a unit of distance that is in terms of meter, and the fundamental units for work is 1 Newton meter or joule, that is given by J. Usually in United States, we are using the imperial units. Imperial units, let me just make this one a little bit bigger. Oops. Yeah, imperial units, the force is measured in pounds. Usually we mention everything in terms of pound, distance that is in terms of feet, right? And the work is measured in lb feet, lb times feet. So here it is, it was not foot, it is meter. Look at over here. Here it was meter and Newton, and here it is LB, feet and LB, or LB feet, you can say. When a constant force F is applied to move an object at distance d, right? Constant force is being applied. Again, suppose I have this one. Suppose I have this one. This is my object. This is suppose one surface. This is my object. This is my object. If I apply the constant force to move this object from one point x equal to a to x equal to b, like this. If I apply some force to move from x equal to a to x equal to b, like this, x equal to a to x equal to b, right? So when a constant force F is applied to move an object at distance d, right? So whatever x equal to a to b that is given to you, that is your distance d, fixed distance. The amount of work performed is W equal to F times d. W equal to F times this, where F is nothing but the mass into gravity, m into g. F is nothing but the mass into gravity. So mass of an object and the gravitational force, that is nothing but your gravity, that is nothing but your force. So keep in mind this thing here, constant force. This word is very important because there are two types of forces. First, we are going to learn over here, that is called the constant force. So again, I repeat, this is very important, guys. Again, if you are not working with this one, that's fine. But keep in mind these imperial units, that is pound in terms of lb, distance in terms of feet, right? And work is lb feet. Okay, distance in terms of feet, pound in terms of lb, so lb feet, that's why. Okay, fine. So when a constant force F is applied to move an object from one point x equal to a to x equal to b, that is called distance d, then the amount of work performed, that is W equal to F times d, where F is measured using the formula m into g. F equal to m into g. M is a mass, g is a gravity. M is a mass and g is a gravity. Okay, guys? Oops. Examples. My first example. How much work is performed pulling a 60-meter climbing rope up a cliff face, where the rope has a mass of 660 grams per meter, right? How much work is performed pulling 60-meter climbing rope up a cliff face, where the rope has a mass of 660. Look at the second example. The second example is just in the continuation of the first example. Consider again pulling a 60-meter rope up a cliff face, where the rope has a mass of 660 grams per meter. At what point is exactly half the work performed? Half the work performed. Okay, guys? So we are doing this thing. Consider of the work performed. Okay, just give me a minute, please. Okay, I think that's fine. Okay, guys. Now, both of these examples, you can see over here, my force is constant, right? Then after, I would like to move to the second part. Second part is over here, Hooke's law and the springs. Hooke's law and the springs. Hooke's law states that the force required to compress or stretch a spring x units from its natural length is proportional to x. That means force is proportional to x. K is the proportionality constant. That is the Hooke's law, F equal to Kx. You are going to use the same formula, F equal to Kx or Ks, in your spring mass system in your chapter 5 of DFQ course. Yes. we are going to solve some differential equations here using Hooke's law when we are looking for the value of the spring constant K. Right, so K is actually here some constant. Actually, there's a proportionality constant. The other way around, I would say that there's a spring constant because Hooke's law that is mainly for spring constant. Look at over here. Hooke's law states that the force required to compress or stretch a spring. Okay, if you want to compress a spring, if you want to stretch a spring, X units. Some people, some authors, they are using S. Same thing. So Ks or Kx units from its natural length is proportional to this one, F equal to Kx. The force of 20 lb stretches a spring from a length 7 inches to a length of 12 inches. 7 inches usually we write in terms of feet, as I told you, imperial units. So 7 divided by 12, 12 divided by 12 like this. How much work was performed in stretching a spring to its length? That means my first two examples, they were based on the constant force, and then after we are doing the variables, right? Force of another examples are there. If you have a printout of this one, that's fine. Otherwise, I would appreciate if you can start your canvas and try to open this packet. I prepared this packet for you from article 7.5, and most likely I'm going to ask you from this packet. So please open this packet, and then after we will go through one by one. So all these examples, yeah, they are based on the work done, right? Now pumping fluids. That is, these are the examples of the fluid mass, fluid flow. Okay, so that is the last article. That's the last article. So for article 7.5 and 7.6, 7.7 actually, I prepared these two packets. So take the printout, try to solve this one by fluid force. Try to solve this one by your own, right? Try to solve both of them by your own. And most likely we'll go over most of the things over here in class. So this is the fluid force. So this is another packet formula. I will explain you everything when the time will come. Okay, some examples. I took varieties of examples over here. Look at here. Varieties of examples are there. And yeah, example 7 or just 5-7 examples, not more than that. Okay, guys. So now let's start with this one. Okay, so work done. Let me start with this work done problem. And that's what actually I want over here. Just give me some time, guys. Give me some time, please. Let me start with this packet. Okay, I think that would be better if we can start all these examples one by one. It will be probably easier for you. Okay, so let me keep this one over here and let me start my my tablet.
Sir,
Yes, please.
do you need to convert, like, the, in these examples, do you need to convert the imperial units to the SI units?
I will let you know. No, you most likely you don't have to. Whenever it is required, I will let you know. Okay, I'm going to take several examples over here. Okay, guys, just give me 2 minutes. Okay, guys. So I think it is better if I start. You have your examples with you, right, guys? So if I ask you to speak the examples, you can speak the example for me. Am I right? So right now we are taking care of first two examples. A first of, sorry. Is it my first two? This is not the first two. First one is this one. This one. Did you open this one in your canvas, guys?
Yes, sir.
Okay. How much work is performed pulling a 60-meter climbing rope up a cliff face where the rope has a mass of 660? Okay, let me share my whiteboard. Let me share my whiteboard, guys. Good. So it is something like this. Look at here. Oops, what is this? Oh. Why I'm getting this one? Sorry. I think this makes sense. Okay. So here you can see, actually, suppose I have a rope like this. I have a rope something like this, and this one is 60 meter. This one is 60 meter. And somewhere over here, suppose somewhere over here, I have a cliff face. I have a cliff face. That means I can start like this. Let X be the amount of rope pulled in. Amount of rope pulled in. This is A-M-O-U-N-T. A-M-O-U-N-T. Amount of rope pulled in. So naturally, what would be my 60 minus X? That is equal to amount of rope still hanging, right? So I can write like this. Amount of rope still hanging. Now length of the rope of mass. So mass is nothing but length of the rope has mass, that is 660 gram per meter, right? 660 gram per meter. If you want to write this one in terms of kilogram, that's fine. That is nothing but 0.66 kilogram per meter. Okay, guys? So that's the same thing. Mass of the rope still hanging. So this is the mass, length of the mass, rope has a mass, and mass of the rope still hanging. So mass of the rope still hanging. And that is given by, yes please, 0.66, if you want to use this one, multiplied by 60 minus x, right? 60 minus x kg. Acceleration due to gravity. So acceleration due to gravity. That is given by acceleration due to gravity. You know that thing, right? Gravitational force is 9.8 meter per second. Right, guys? So what is my force? Force equal to M equal to A. I told you. That means your M is nothing but this one, still hanging. So 0.66 multiplied by 60 minus X multiplied by A is a gravitational force. So 9.8 kilogram meter per second square. And that is nothing but your Newton. So my W is now, my W is a work done. So work done is equal to integration. How much? Starting with X equal to 0 to 60, right? Length of the rope. And f of x dx. F of x dx, this is f, or you can see it's a function of x. F of x dx. And that is equal to integration x is equal to 0 to 60 and 0.66 multiplied by 60 minus x multiplied by 9.8. 9.8 is a constant, you can pull it out. 0.66 is a constant, you can pull it out. If you multiply this 9.8 by 0.66, you are going to get something. 9.8 means almost, it is 10 and 0.66. So it would be if I write like this, 8 and then I would say 6 and I would say 4, 8 and then 60 minus x. So this is 996, 54 and 9, so 64. So it is 6.468, something like that you're going to get. That's the constant. Let me pull it out. Now x is equal to 0. You can use your calculator to get this one. You don't count like me, please. Don't count directly. And that is, here it is 60 minus x and here it is dx. Now you can get the answer that is equal to 6.468 and here it is 60x minus x squared by 2 and range of integration is 0 to 60, and whatever you're going to get, that would be your answer. Here it is 0 and 16 multiplied by 60, that is 3600, 3600 and minus 3060 squared, 3600, 3600 divided by 2 means 1800, right? So 36 minus 18, that is equal to 18. So that means point this one, and then otherwise it is 0, right? So whatever you're going to get, that is your answer. Just use your calculator, write down your answer. And here we have used the empirical units, that is joule or Newton per meter. So I would like to say that is equal to joule, or you can say Joule or just joule, or you can say that is equal to Newton per meter. So that is the answer of the first example. Any doubt? That is the answer of the first example. Any doubt, guys?
No, sir.
Okay, Ismail, will you please read the second example for me from the packet? Ismail, read the second example.
Yeah, sir.
Go ahead.
Consider again pulling a 60-meter rope up a cliff face, where the rope has a mass of 660 grams per meter. At what point is exactly half the work performed?
Right. It says something like this. Okay, fine. For that, I need the answer of this one, because it says that half of the work done. So this is my work done. This is whatever the blank line I just left for you. This is actually my work done. This is my work done. This one. So is anybody can anybody use the calculator and give me the answer? This one, by replacing x by 60. So it is 1800 actually. 1800 multiplied by this one. Give me this number. 1800 multiplied by this 6.468. You can use
11,642.4.
11,640.
2.4.
Right? Okay. Thank you, buddy. Thank you. Appreciate. Okay, fine. Now, our second example says that, as Ismail, he read the example for us. It says that the half the work done. May I erase this part, guys? I don't have anything to say over here. It's hard. May I erase this one? If you want, you can take a picture of this one. You can take the picture so that I can for the next slide. If you want, you can take the picture. Otherwise, I'm good. Shall I move ahead? Shall I go ahead? I'm waiting, guys, girls.
Yes, sir.
Yes, sir.
Yes, sir.
All good.
Virginia, are you okay? Virginia, are you
Yes,
okay?
sir. I'm good. Thank you.
Good. Judith is still not here, right? Okay. Alexis, Davis? Davis, Alexis? Okay. Okay, guys. So let's go for, let me clear my screen. So just remember this last number, please. 11,642.4. Okay, good. Let me clear this one. So clear all things. Let me start now this one. The second example. Half the work done. My gosh. half the work done. That means equal to, how much it was? 11,642.4. Am I right? Divided by 2. Soto, please give me the answer.
Yeah, that's correct, sir.
Say again. Say again.
Correct.
Correct. That's the number. You're good.
Yep. So what is the number? 11,642 divided by 0.4 divided by 2. So you're going to get something.
582.1.
521.2 joule. Okay. Am I right?
Yes, sir.
Yes or no, guys? Now,
Yes, sir.
Find a height h such that the work is pulling the rope from x equal to 0 to x equal to h is this one. The half of the work done is given to you, right? And what we want to find that height h such that the work in pulling the rope from x equal to 0 to x equal to h, that is equal to 5821.2, half of the work done. That's the meaning. Let me write it down for you. Probably that will give you more sense. So we want to find a height. We want to find a height such that, this is the symbol of such that the work in pulling the rope from x is equal to 0 to some height, x is equal to h, which we are looking for, is 5821.2 joule. That is the meaning. That means I am looking for integration 0 to h. Yeah, my last integral was 9.8, 0.66 if you remember, and it was 60 minus x and dx, and that is equal to, work done is given to you, 5821.2. Solve this one. This is your values of x. X runs from 0 to h, so you can find your h. And as I told you, what was my this constant, this one and this one? This constant value was 6.468, right? So let me just pull it out. An integration 60x minus x square by 2, and the range of integration is 0 to 8, that is equal to 5821.2. So this implies that this will remain as it is, and here it is again the same number. So 6.468 multiplied by 60h minus h square by 2 equal to 5821.2. Let me divide by this number 6.468, right? Let me divide by this number. If you divide by this number, what I'm going to get? Just use your calculator and give me the number. Use your calculator and give me the number. So that is equal to 60h minus h square by 2 equal to some number. Give me that number, guys, please, quickly.
900 for the answer, sir.
That sounds good. So it is 900. Yeah, it was expected. Yeah, 900, right? Good. Now, if you take the LCM over here, you're going to get that is equal to h square, right? H square minus 120 of h. Yes or no, guys? H square minus 120 of h plus multiplied by 2. So 1800 is equal to 0. So I'm getting the quadratic equation. Look at here. Sorry. I'm getting the quadratic equation. It's a quadratic equation. So that means I can find my h equal to negative b. So it is negative positive plus or minus square root of b square minus 4ac. So b square is 120 square is 12 square is 144 and 2 zeros minus 4ab. So a equal to b equal to 8, c equal to 1800. So 18 fours are 72 and 100 and divided by 2. You please use your calculator. Don't count like me, please. And that is equal to 120 plus or minus. Here 144 minus 700 will be, give me this number, guys. Please use your calculator. 14,700 minus 7,200, right? So it is 7,200 and square root. So square root will be something 80, I don't know. Use this number, give me the square root. You're going to get something
84.85.
85. Okay. and divided by 2, right? Now, first one time you take plus sign, then after you get you take negative sign. 120 plus 84. 120 plus 84 will be 102.85. Am I right, guys? If you divide by 2, actually it is 204, and so divided divided by 2. So here it will be 43. Here it will be 43. 102.43. And second time you're going to get your h equal to, this is my h. And if you take minus sign, so 84 and 16 and 20, so 36 divided by 2 and 0.85. So almost you're going to get, use your calculator, what? Something 17 point something? 7 and 5 and 84.
17.53 or 57.
57. Okay, 17.57. Which answer is good out of these two? Make sure, since the length of the rope is 60 meter, right? And here it says that length is 100. Is it possible that you can increase the length of the rope? No, it's a fixed number, right? So your answer at the half work done must be in between from 0 to 16. So this 17.53, whatever we said, that makes more sense. This makes more sense. This doesn't make sense. So please cancel this answer, and your answer, that is equal to, h is equal to 17.57, whatever it says, and it is given in terms of meter. So don't forget the unit. So this is the answer. Does it make sense?
Yes, sir.
Yes, sir.
Right, guys? Good.
Yes, sir.
Good. Good. Shall I go ahead for the next example? Shall I go ahead for the next example, guys?
Yes, sir.
Yeah, absolutely.
Good. This is the mathematical symbol of such that. Please keep in mind this thing, such that. Reverse epsilon. Okay, so let me clear this one. And now, then after we just went to Hooke's law, I told you that Hooke's law is nothing but F equal to Ks, where K is a spring constant. So F is force is directly proportional to the distance, right? Or stretching or compressing of the spring. And that's why it is given like, this one, that W is equal to integration of f of x and dx. X runs from 0 to some number x, and where f is nothing but capital F or small f, whatever you want to say, that is equal to k times s. Some people say k times x, where x is nothing but the stretching of the spring. Natural length is proportional to this one. Okay, then Nick, Tony, please go ahead and read the first example for me.
Yes, sir. Sorry, let me just find it real quick.
Yeah, after the Hooke's law, read the first example for me after Hooke's law. Hurry up.
Sorry, it's let me just get this.
Christopher Janel, read the example for me.
Sir.
Hurry up, guys, please. Don't waste our time, please. Christopher Janel, please. I told you, please keep that one open. Why are you not following me?
A force of 20 pounds stretches a spring from a length of 7 inches to a length of 12 inches. How much work has performed in stretching the spring to this length?
Right, that means it is like this. Look at here, guys. The length of the spring was 7 inches, and if you apply the force, if you put some weight on free end of the spring, that means it is stretching the spring, right? A little bit more. So now the length is 12 inches. Are you getting me? That means the stretching is nothing but 12 minus 7 means it is 5 inches. Am I right? The stretching is 5 inches. It is something like this. Look at over here. Suppose I have one spring which is hanged at one end, and second end is, oh my gosh, this is my spring, and this is the free end. This length is given to you, that is equal to how much? 7 inches? 7 inches. And if you put some weight over here, that means it will be stretching a spring a little bit like this, right? After putting that weight, and it will jump like this, and it will come to the equilibrium position. And this motion you're going to find in your DFQ course as an application of second order differential equation. The stretching is nothing but stretching the spring, how much? 5 inches? How much there was? 12 inches, right? Stretching the spring 12 inches. That means the total length is now 12 inches. That means this length is 12 minus 7, that is equal to 5 inches. 5 inches, that means I can write 5 divided by 12 feet. Agree? So stretching the spring, and this stretching the spring, that is nothing but the, yes guys, what is that? This stretching the spring, that is nothing but your x. So your x equal to 5 by 12 feet. So in Hooke's law, this capital F or small f doesn't make sense. Sorry, that's the same thing. F equal to kx. Force is given to you. Force is equal to 20 lb given to you. K, you are looking for spring constant. And 5 by 12, that is my x feet. Right? So naturally my K equal to, what is K? lb per feet. So it is 20 divided by 5 times 12. And here it is lb per feet. So K is always in terms of lb per feet. Please keep in mind this thing. So 20 12s are 240 divided by 5. 240 divided by 5 means 48. So 48 lb per feet. So 48 lb per feet, that is my K constant, spring constant. Go back and plug this value of K over here in my formula. So F equal to now 48 of X. This is my F, or you can say Fx. But what is my work done? My work done is nothing but W is equal to integration X is equal to 0 to what is given to us? 0 to 5 by 12, right? 0 to 5 inches. X equal to, this is my 0 to here 5 inches. So 0 to 5 inches. And here I can write that is equal to F of X and dx. F of X and dx. That is equal to X is equal to 0 to 5 by 12. And F of X is nothing but now 48 times X and dx. 48 is constant, pull it out. Here it is X square by 2, 0 to 5 by 12. Just solve this one. And this is 24. And 25 divided by 12 square is 144. So that means whatever you're going to get, that is your answer. So I don't know what is that, but that is equal to feet times, what is the unit? Feet times lb. Agree? Feet times lb. So that is the unit. So please use your calculator. Whatever you're going to get, that is your feet times lb. So that is the answer. Any doubt? Any doubt, guys? Example number 2 and 3, they are just similar to this one, exactly similar to this one, only values are different. So please try to solve this example 2 and 3. I want somebody to speak the example, John Marshall. Speak the example number 2 and then 3, and then we will switch over to the fourth example. Example number 2 and 3 first. Go ahead. John Marshall, where are you? People are, John Marshall.
I just ran to the bathroom, sir. I just came back right now. Ooh, very quickly.
Speak the example 2 and 3.
Number 3, a force of 100 pounds compresses a spring in 3 inches. How much work is performed in compressing the spring?
Right, guys? Example 2. Go ahead. John, go ahead. Example 2.
That was the second one, I think.
That
was the second one.
What is example 3?
Go down and it's the next one.
A force of 50 pounds compresses a spring from 18 inches to 12 inches. How much work is performed in compressing the spring?
Okay. See here, both the examples, they are just similar to this example, whatever you can see over here on the screen. Okay, guys. And John, again, what is example number 4 now?
Example number 4, a force of 7 newtons stretches a spring from 1170.
Repeat, slowly.
A force of 7 newtons stretches a spring from 11 centimeters to 21 centimeters. How much work is performed in stretching the spring?
Okay. So, force, repeat the example. 4 equal to how much force is there?
7 newtons.
7 newtons. Okay. And then?
And then it's the stretch the spring from 11 to 21 centimeters.
So 21 minus
11
centimeters, right? I have to, because it is Newton, so I have to convert this one in terms of meter. So that is equal to 10 centimeter and that is equal to 0.1 meter. Again, 0.1 meter. Now F is equal to Kx. F equal to Kx. It is given in terms of Newton. Just keep like this Newton, and here it is we converted to meter. So here it is 0.1. So this implies that my K is equal to 70 Newton per meter. Agree? Just go back and plug that value of K over here. That means I'm going to get F equal to, help me, sorry. F equal to 70. This is 70, okay? F equal to 70x, right guys? So naturally my work done equal to integration, x is equal to 0 to, it goes to 0.1, right? Look at what you're stretching the spring in terms of meter, and fx is nothing but of 70x and dx. That means 70 and x square by 2 and integration 0 to 0.1. Whatever you're going to get, that is the answer in terms of joule because it is given in terms of Newton. That's why your final answer that is in terms of joule. Joule is nothing but Newton per meter. You know it, Newton meter. Joule, or you can write Newton meter. Easy?
Yes, sir.
Hello guys, good. So all these examples, whatever we solved so far, all those 4 examples, they are based on constant force. Whatever we did so far, whatever the examples we did, all these examples, they are based on constant force. Now we are going to say the variable force. I mean to say that increment, force increment, or you can say variable force. So let me remove this part and let's go for the next one. So next part is variable force, or you can say force increment. Variable force or force increment, right? I want somebody to read the example. Who is there? Virginia? Virginia.
Which example is this, sir?
It is the force increment first example.
Okay, hold on.
Force increment first example.
You said 5th increment?
Force increment, force.
Hold on. My PDF isn't loading.
Okay, Thomas Williamson. Thomas Williamson.
Yes, sir.
Go ahead.
Is
Yes.
a cylindrical storage tank with a radius of 10 feet and a height of 30 feet is filled with water, which weighs approximately 62.4 pounds per feet cubed.
Okay, that's the density, right? Density. Now, whenever you are working with the force increment example, at that time, some liquid will be there in your vessel, and that's why the density of the liquid will be provided to you. It will be there in your example. Without that density, you cannot move ahead. You cannot go ahead. So please make sure that density of the liquid, whatever liquid is there, water, mercury, whatever it may be, but that density will be provided to you ready-madely. Go ahead.
Compute the amount of work performed by pumping the water to a point 5 feet above the top of the tank.
Right, guys. Can you please repeat the same example, Thomas, please?
Yes, sir. A cylindrical storage tank with a radius of 10 feet and a height of 30 feet is filled with water.
Wait. One tank is there. Cylindrical tank. One tank is there. Radius is 10 feet, right? Radius 10 feet. That means radius of the tank means upper circular part is 10 feet. It's like this. So circumference over here, that is 20 feet. That is 10 feet. Now, height of the tank is 30 feet. That's what given to you, right? Height of the tank is 30 feet. What is 30 feet? Please go ahead.
Which weighs approximately 62.4 pounds per feet cubed.
That is the water density. 62.4 pound per feet cubic feet. That is the water density. Okay. So water is there inside the tank, and we want to pull this water out. That means we have to perform some work. Are you getting it, guys? One tank is there. Size of the tank is given to you. Radius of the tank is given to you. Level of the tank, level of the water. Some water is there in the tank, and we want to pull this water out using some pure something like that, right? So what is the work done? And that, yes, go ahead, please. Density is 62.4 lb per feet cube. Then
compute the amount of work performed by pumping the water to a point 5 feet above the top of the tank.
Above the top of the tank, right? Now, this is your tank. This is your tank. Above 5 feet. 5 feet above, you have one instrument, pumping machine, which pumps your fluid your water from the tank, that means you require to apply some work, and that work done we are going to measure. So that's the problem. Would you understand this thing? Could you understand the problem, guys? And that is called the force increment. That is called the force increment. Do you understand the problem, guys?
Yes, sir.
Yes,
Okay.
sir.
So let me start this problem now. So look at here, guys. In this problem, I draw the picture, but usually you will not be provided the picture. You need to draw the picture by your own. If the figure is not given to you, only the informations will be given to you. Here, it says that 10 feet cylindrical tank. So cylindrical tank, oh my gosh. What is this? Okay. Cylindrical tank, right guys? Like this, cylindrical tank. Okay. Something is over here to pull out the water inside the tank. And this is my water. This is my water. What I'm going to do, I have to use, look at here guys, please. Do I have any colors over here? I want to use different colors. Spotlight, eraser, format, yes. Yes, 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 okay. Now I want to take the cross-sectional portion because we don't know how much level of water is there in the tank. We don't know how much level of water is there in the tank. That means I'm going to take one cross-sectional part over here, and that cross-sectional part, it's something like this with some small height of that cross-sectional part. With some small height. Look at here, guys. This is the cross-sectional part. Now, look at here, guys. This one is given to you. Here to here it is 10 feet. 10 feet. Height of this cylindrical tank is given to, I think, 30 feet. Am I right, guys, if I'm not wrong? So this one is 30 feet. Yes or no, guys? William? Thomas?
Yes, sir. It's 10 feet.
That is 30 feet. This height is given to you that is equal to 5 feet. So this height is 5 feet. Means total height from here to here, that is equal to 35 feet. 35 feet. Agree, guys? As I told you that we don't know the level of the water, so that's why I just would like to consider something, some height, and I would like to consider this height that is equal to suppose some y. So that is in vertical direction, so there is some y. We don't know, that's why just y. It could be here, it could be here, here, at this level, this level, this level, we don't know. That's why I would just like to consider this one as y. This one, this is, I would like to consider as y of I. And this upper part, this is the lower part, y of I. And this upper part is y of I plus 1. So this difference will be given to us, that is called delta of yi. Small change, very small change in the layer of the water, that is delta yi, that is equal to yi plus 1 minus yi. Why I used I means it's ith level. It could be first, second, third, fourth, fifth, because you know, every liquid has some layer like this, right? So we are working with the ith layer. It could be the first layer, second layer, third layer, what it may be. But delta yi is this one. Delta yi is this one. One more thing. Total height over here of this pump, that is from the bottom of the tank, that is 35. And here it is 5 feet. So naturally, what could be my height from, look at here, from here to the water level. Water level is here. Water level. So this height is nothing but, I figured it out, this height is 5. Total height is 35. So naturally this height is 35 minus y. Am I right? 35 minus y. Yes or no, guys? So that's how the picture. You have to draw the picture. You have to put all your values like this, whatever I drew over here. And then after you can start your example. So my example, I can start like this. Water density water density that is given by rho, and that is equal to, here it is 62.4. There's a standard density. All these numbers are fixed, comes from chemistry. So 62.4 and lb per feet cube. You have to mention all your units, lb per feet cube. First of all, I would like to find the volume of this cross-sectional part. So volume of this cross-sectional part is given by VI. Now, what is the volume of the cylindrical tank? Pi r square h, right? Pi r square h. So volume of this cross-sectional portion, that is also one kind of cylinder, right? So that is also pi r square h, but here it is pi and then r square, and your h is the height of this layer. That is, I wrote it down by delta y. So let me write that times delta y. Pi as it is, r is the radius of the tank. So radius is 10 square, and delta y, that is equal to, what is my delta y? Delta y as it is. Delta y, that is as it is. So this is my VI. Now I'm just working on this cross-sectional portion, guys. F is equal to nothing but mass into volume. Mass into volume. This cross-sectional volume. Please keep in mind this thing. Mass is nothing but your density. Mass of the density of the water, that is your mass. This is actually your mass. So mass is given to you, that is equal to 62.4 lb per feet cube, right? Times, here it is, volume is 10 square is 100 pi and delta y. 100 pi and delta y. That is my F. So what is my W? If you want, you can write F of I. So but what is my work done? Work done, that is equal to F or F of I times distance. You know this thing. Force times distance, that is the work done. But again, this is not my W. I would say WI, because I'm just working with the cross-sectional portion. So Fi times D. Fi, that means this one, multiplied by 62. 62 means 6240. So let me write 6240 pi, and this distance is, what is my distance? Distance from here, look at here, distance from here to here, pump, that is 35 minus y. So 35 minus y. Distance from here to here, that is 35 minus y. This Wi is nothing but 35 minus y, and 35 minus y, and this delta y, and this delta y. If I'm going to take all this type of cross-sectional portion, try to pay attention, guys. This is just one cross-sectional portion. One layer, second layer, third layer, fourth layer, below this one. If I count all these layers, that means I am just summing up all these layers. That means I'm going for the integration. And that means I would like to write, where is my cursor? Yeah. So that means I'm going to write W is equal to integration y equal to, height of the tank is 30. So y equal to 0 to 30. And this Wi, you can say Wi dy. Wi dy. Wi actually is this one. So y is equal to 0 to 30, 6240 pi, 35 minus y. And this delta y is the height of just one strip, you can say, or just one thin layer. If you sum up all these kind of layers like this, 1, 2, 3, 4, 5, 6. So we are just adding up all these layers. So this delta y, that will be converted to d of y. And that is equal to 6240 pi constant. Let me pull it out. Integration 35 with respect to y. So 35y minus y square by 2. Y runs from 0 to 30. And then use your integration. Whatever you're going to get, that will be your answer. Your unit will be lb feet. Your unit will be lb feet. Any doubt? So this much of work is required to pulling your water up to the tank, where your pump is 5 feet up the tank, and height of the tank is this one. If you have any question, you can ask me. In short, it's not a rule, but in short, look at over here. Whenever you are working on x-axis, integration with respect to x, at that time, your force is constant. But whenever you are pulling the water, or you are pulling the water from the well, from tank, something like that, at that time, means you are working along y-axis, integration with respect to y, your force increment. force is invariable. Any question, guys? Here, of course, you're going to get very big answer. If you want something like this, suppose you have some answer, I don't know, but suppose something, 1 point something, blah, 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 and you can write 10 to the power something, 7, 6, what it may be. So please write the answer in form. Don't write such big answer. Just write your answer in a compact form. Any doubt? Any doubt?
No, sir.
Okay, guys. So let me do this thing. Let's go for the example number 2. Who wants to take this example 2? Example 2 is exactly similar to example number 1. Mass is given to you 45.93 lb per feet cube. V equal to pi r square h. Right? Let me share my screen with you if you want. May I erase this part, guys? Stop sharing and let me share the another screen. That is this one. So my second example, then after Hooke's law, first example, 1, 2, 3, 4 examples are there. And then after we started with the pumping fluid. So pumping fluid, you can see over here, different weights and mass of the density of the different density of different liquids are provided to you over here. Whatever liquid you are working with, that density will be given to you in the example. Look at over here, kerosene, iodine, methanol, mercury, milk, water, whatever it may be, right? So all of these are given here. And this is the first example we finished right now. Does it make sense? A cylinder.
Yes, sir.
Yeah, look at here. Right, guys? This is the example. Shall we go for the next example?
Yes, sir.
Tall cylindrical tank. Now the height is 5 feet. With radius of 2 feet. Instead of 10, now it is 2 feet. It's filled with 3 meters of gasoline. Now the liquid is gasoline, whose density is 45.93. That is given to you. Density is given to you now. 45.93 lb per feet cube. lb per cubic feet. Okay. Compute the total work performed in pulling all the gasoline to the top of the tank. Right? Look at over here. Here I have not provided you any figure. That was just the first example. That's why I give you the figure. Here there is no figure. That means you are supposed to draw the figure. You are asked to draw the figure. Let me again share my screen. Just keep this one in mind, that 5 feet tall cylindrical tank for this is density and radius is 2 feet. Okay, I got it. So let me stop sharing this one. Let me share my screen. Okay, may I erase this part, guys? My previous example?
Yes, sir.
John liked this whiteboard, right?
I do. I appreciate it very much, sir.
Thank you. Okay, guys. So my next example is, yes, my mass is given by rho, and that was how much? 45 point. How much, guys? 45 point.
45.93.
Okay. So if I draw the picture, you have to draw the picture, I told you, right? Okay. The height of the tank is 5 feet. So this height is 5 feet. One cross-sectional portion over here of gasoline. This is the gasoline. The cross-sectional portion is over here. Gasoline part. Right? This is my delta Y, I, that is equal to Yi plus 1 minus Yi. We know this thing. Okay. And now I pump. This is my 2 feet. Radius is 2 feet. Pump is just over here. So it's not on top of the tank. It is just over here. Right, guys? This is 5 feet. This distance usually we measure by y. I told you that you can assume, you can always assume that this distance is some y. So assume this distance is y. So naturally this distance is 5 minus y. This distance is 5 minus y. That means I can write directly now my volume V equal to pi r square and h. Pi r square is 4 and h is equal to delta y. H equal to delta y. So that means my F is equal to mass into volume. Mass into volume. So mass is given to you 45.93 times volume, that is equal to 4 pi and delta y. 4 pi and delta y. Mass is given in terms of lb per feet cube, and volume is given to you in terms of feet cube always. That is equal to lb. So your unit is lb. Your unit is lb. Okay, guys, fine. So my work is, or I would say Wi, that is equal to F times D. F is equal to this one, 45.93 multiplied by 4 pi, and distance is nothing but 5 minus y, and this delta y is converted in terms of dy, or I would write delta y over here. That is just for this cross-sectional portion. So total work done, that means we are going to sum up all these type of layers. That means integration y equal to 0 to 5, because that's the height, and f times d, that is equal to f times d. Yeah, you can write like this. So y equal to 0 to 5 and f times d, wi equal to 45.93 4 pi and 5 minus y, and delta y is converted to dy. All I constant, I would like to pull it out. So this is this one, and here it is 4 pi, and here it is, sorry, oh my gosh. And here it is 5y minus y square divided by 2, and here it is 0 to 5. And whatever you're going to get, that is your answer, lb feet. That is your answer, unit lb feet. Sounds good? Any doubt?
Yes, sir.
Any doubt?
Sounds good.
So nice. If you want, you can take the picture so that I can switch to the new example. I can switch the new example, right, guys? I think example number 3 is now cone. It's quite important. It's now cone. So we have to be very careful about this one. Example number 3. And I think that would be probably more than enough for today, because I think most of the things are done. So work done will be done after this example, and I would like to stop, and tomorrow we'll be doing the article 7.6, that is a fluid force. So let me go through this last example now, and we'll stop. Last example. May I erase this part? Rachel, you are still writing, right?
Oh, no, I'm done, sir.
Okay. Anybody want some more time?
No, sir, you're good.
Jonathan Soto, why are you so quiet today?
Oh, we're good. Yeah, I'm good.
You're good.
Just writing.
Okay. That's fine. Virginia is good, right? Virginia?
Yes, sir. I'm good.
Where are you?
I'm right here.
Okay, Virginia, you need to work hard. You know this thing, right?
Yes, I do.
Yeah, please work hard. And if you need my help anytime, you're most welcome, okay?
Thank you.
Yeah, because I know you were not here in the first week almost.
I do have one question. Since I missed the first test and you let me make it up, I had emailed it to you because the submission wasn't open, but you still haven't graded it. Did you just never get that?
I know. I'm going to send that one to you very soon, okay? Just give me some time. I'm too busy right now.
I can, well, I understand that, like, no rush. But if you never got it, I can re-email it to you.
No, I got it. I think I got it, but let me double check today. If I get it, I will let you know, okay?
All right. Yeah, just shoot me an email. Thank you.
That's fine. No problem. Work hard, guys. Work hard. I'm with you. Just work hard. Okay, so let me erase this part and let's go for the next one. So let me just stop sharing this one. Stop sharing. And let's go for here. Let's go for the screen. So next example is this one. Again, I gave you this picture, but actually we need to draw this picture. Who wants to? Powell, would you like to read this example? Powell, Vocal Powell. Powell, please read this example for me. This is not fair, Powell. Why you guys want to upset me? I don't know. Matthew Alberston, read this example for me.
A conical water tank has its top at ground level and its base 10 feet below ground. The radius of the cone at ground level is 2 feet. It is filled with water weighing 62.4 pounds per feet cubed.
Big field.
And is
Okay.
to be emptied by pumping the water to a spigot 3 feet above ground level. Find the total amount of work performed in emptying the tank.
Right, guys? So instead of cylindrical tank, now you have a conical tank. Conical water tank has its top at ground level. So it's a reverse wave. Conical tank at the top at the ground level. So like this. And its base 10 feet below ground level. Right? It's base of 10 feet below ground level. Base of 10 feet. Base of 10 feet below ground level. 10 feet below ground. Ground level is 0. 10 feet below ground level means it's negative 10. Am I right? It is below the ground, so it is negative 10. So that's why it is negative 10. Please keep in mind this thing. The radius of the cone at ground level is 2 feet. At ground level, it is something like this. On the ground, one tank, you can only see the top circular part of the tank, and whole cone is inside the ground. And that height of the ground, height of the tank, not tank, height of the cone is 10 feet. So that's why we are using negative 10. Okay. The radius of the cone at ground level is 2 feet. If it is filled with water weighing 62.4 lb per feet cube density, and it is to be emptied by pumping the water to the spigot 3 feet above. So this is my ground level. I can see only the mouth. I can see only the circular portion of the cone on the ground. And I have to take my spigot 3 feet up above the ground level to pull my water, or maybe water out. So find the total amount of work performed in emptying the tank. Again, we are working in the vertical direction. Look at over here, guys. So just it is 2 feet, this one, and spigot is 3 feet high, and this one. Okay, so let me again stop sharing and let me share my screen. I want all of you to keep your example in front of you from Canvas. Okay, so clear. And now it says that something like this, guys. Okay, and this is my ground level. This is my ground level. Okay, my spigot is 3 feet above the ground level. So this one is 3 feet. This one is 3 feet spigot. Spigot. Right, guys? Now, this distance is given to us that is equal to 10 feet. 10 feet. Because it is underground, so I would say it is, if you want, we can say it is negative 10 feet. So, or you can say 10 feet, I don't mind. It is up to you. 10 feet. I have to have one cross-sectional area over here. One cross-sectional area over here. Right? Whatever the distance I have from here to here, from the cross-sectional area, usually we assume this distance. But at that time, my tank or cylindrical tank, everything that was on the ground. Right? Right now it is below the ground. So that's why I would like to consider this is negative y. This one is negative y. This distance is negative y. I have this point. This point is 0 because if I write like this, look at over here, just try to visualize like this. This is my y-axis and this is my x-axis. So this point is 0, 0. This point is 0, 0. So here this point is axis 0, same thing, and here it is negative 10 because it is below the ground level. Agree? Negative 10. And this radius is given to you, that is equal to 2 feet. Radius is 2 feet. That means this one is 2 and 0. That means I would like to consider this one of these points, that is x1, y1, and second one I would like to consider as x2, y2, so that I can get the equation of this line. Using these 2 points. I can get the equation of the line. Why I want the equation of the line? I will let you know. Here, see in the cylindrical portion, what I had, whatever cross-sectional section I chose, that cross-sectional section had same height, same width. Am I right? Because the tank was cylindrical. But now the tank is conical. That means my upper layer and the lower layer of my cross-sectional part is different. Are you getting me? It's a small difference, but the difference is there because it's now it's a conical flask, conical layer, conical tank. Are you getting me, guys? So if you have something circular portion, if you are taking some cross-sectional part, and if you take very thin height, at that thin height, upper height and lower height has the different dimension. Because of that, you cannot use that fact, whatever we have used for the cylindrical tank. But I'm interested for y. I have to have some function of y. So that's why I just fix these 2 points and try to figure it out. I'm going to figure it out, the equation of line. And then after I'm going to make the equation of y using that equation of line. Good. So what is my slope first? My slope m equal to y2 minus y1 over x2 minus x1, right? So y2 minus y1, that is equal to 0, minus minus plus. So 10 divided by x2 minus x1. So that is equal to 5. Agree? That is equal to 5. So what is my equation of line? Y minus y1, that is equal to m times x minus x1. Y minus y1. Y minus y1 is, so y plus 10. That is equal to 5 and x minus x1 is 0. So y is equal to 5x minus 10. Am I right, guys? Y equal to 5x minus 10. Yes or no? But we want actually a function of y. We don't want a function of x. We want a function of y because we are integrating. It's a vertical line, vertical way. So we are integrating with respect to y. So this implies that I am writing x is equal to actually y plus 10 divided by 5. So x equal to, so you can come directly from here to here. X equal to y plus 10 divided by 5. Y plus 10 divided by 5. Now let me start with my example. So these are the informations provided to us, and I ended up with this one. Now my volume V, volume of the cross-sectional part VI equal to, what is the volume of the cone? 1/3 pi r square h. Agree? That is equal to 1/3 pi, r is equal to 2. So 2 square, is it 2? Yeah, that is equal to 2. So 2 square, and my h, my height is, what is my height? My height is nothing but this one. So whatever h you fix, that is here, or actually pi r square and h is my height of the cross-sectional portion, right? So that is equal to delta y, I would say, delta y. And my r is nothing but, this is not my r because I'm talking about my this distance, this radius, this distance, this x distance. Actually this one, look at over here. This is my x. I'm looking for this x. And this x is over here. Please try to pay attention. This x is over here. And this x changes every time because my cone, it's a cone. It's not a cylinder. So this x changes. See here, it was 2 over here. So this x, whatever I am having over here, that is less than 2. If I go over here, it is still less than this number, still less than this number, still little greater than this number over here. If I take some portion over here, some cross-sectional part over here, right? But it would not be more than 2 because 2 is the maximum radius. So this x, that is something less than 2 and greater than 0, something over here. So you cannot write by radius over here because we are taking the volume of the cross-sectional portion. So whatever I mentioned over here, that is actually the wrong thing because that is for the whole cone, top part. No, we are taking the cross-sectional part. That means my r is nothing but this one. So I would say that my r is equal to this one, y plus 10 by 5. So let me write it over here, y plus 10 divided by 5 and square is that, and square. Right, guys? So now my F is equal to mass into volume. Mass is given to you 62.4 lb per feet cube. Volume, just now I figured it out, that is equal to pi over 3. Pi over 3. And here it is, I can write y by 5 plus 2 square and delta y. Unit is lb per feet cube and volume is always feet cube because this is feet cube. Feet cube, this will get cancelled, so it is simply lb. Now my W is equal to, now I'm pulling from this one, the bottom part. So it comes from here and goes in the vertical way. That means y runs from -10 to 0 because this is here y equal to 0. And my force times D. Force times D. So that is equal to y is equal to -10 to 0. My force is equal to this one. Help me. 62.4 pi divided by 3. You can pull it out. You can pull it out. And here it is y by 5 plus 2 square. And here it is dy. And here it is dy. Something is still missing, right? What is missing? This distance. Whatever I wrote down, that is just f. This distance is missing. And this distance I would like to incorporate over here. This distance is, what is this distance? Don't forget this one, 3 feet above this one. This distance is y. This distance I assumed it is -y. So total distance is adding this one and this one, so 3 minus y. So my distance d here, that is equal to 3 minus y. So let me write over here that is equal to 3 minus y. Don't forget this part. Okay. Now the ball is in your court. That is equal to 62.4 pi divided by 3 constant. Pull it out. Integration y equal to -10 to 0. Y by 5 plus 2 whole square and 3 minus y and dy. So first take a plus b whole square here and 3 minus y, just term by term multiplication. Just multiply this one and then go for term by term integration and that will give you the answer. So that is your homework. That is your homework. That will provide you the answer. And you know this thing that answer is always in terms of feet lb. Feet lb, that is the unit. Does it make sense, guys?
Yes, sir.
And
Yes, sir.
if you have any doubt, you can ask me right now. If you don't have any doubt, and tomorrow I would like to start the next article, that is a fluid force. Is it okay?
Sounds good, sir.
Okay, guys, thank you so much. Please work hard. Those who have not submitted your homework or taste what it may be, excuse me, please do it very quickly. And let me stop sharing the screen and I will see you guys tomorrow. Sounds good?
Sir, can I tell you something real quick?
Sure, go ahead.
So I'm flying back to my house in Virginia tomorrow, and so I won't be able to go to class tomorrow morning. But I can watch the lesson on YouTube once you upload it. If
all you guys, you want to watch this thing? That sounds good. But I have one request for you. How many of you have gone through the videos? Some of you, I think so, right? Not all. How many of you are using these videos? If it is helpful to you, then I can download all the videos. But if it is not helpful, if you are not using that one, then in that case, I think there is no purpose to downloading the videos. What do you say?
well, I'm not sure what the rest of the class has been doing, but I know for me personally, since I've been present to all of your classes, except for the one last week since I was flying, I personally haven't had to use the videos that much, but it for this situation would help. But if it's too inconvenient for you, then it's fine. I can just look through the notes.
Okay, no problem, guys. I'll do that favor for you. But please keep in mind this thing, that please subscribe that channel and click on the bell icon so you will be notified when I upload some new things. Okay, so you're notified and immediately you will get one by one all the videos and everything. You don't have to open that thing very frequently every time. So please do this thing. Thank you, guys. Thank you so much. And
thank you. I'll email you too, just to let you know. And
that's fine.
but okay. Thank you.
Thank you. Yep.